seria controladíssim.
Ella és la Nayanika i el seu estudi és on the peroxidase activity of Mammalian Glutathione Peroxidase. I el seu treball està escrit en el programa de doctorat en Bioinformàtica i el director de la seva tesi és el doctor Jordi Villar i Peix. Jordi Villar, perdó.
Hi everyone. Okay, let's begin with understanding what are. Oh, okay. Do I have to start?
Perdó. Ara sí, espera. Ara.
Yeah, so let's begin with the story of molecular simulations and evolution that come together here. So we all know that we have a lot of proteins in our body, and we know that each protein is doing some function, specific function in the body. So in the same way, I focused on one of the proteins, which is glutathione peroxidase. There's nothing to be scared about it. It's a good protein. So what it does is, you can see two faces there. There's a smiley and there's a sad face. So the smiley face is the one where GPX actually it controls the oxidative stress in the cells. Because we don't want our cells to be stressed, because when they cause a lot of diseases, like it can lead to cancer, it can lead to early aging. Well, we know that we don't want early aging, right? So these radicals on the left hand side, they make it cause these diseases. So GPX actually protects them. It maintains a balance. How does it do it? So it has two different chemicals that helps doing that. One of them is selenocysteine and the other one is cysteine. So a sulfur and a selenium. That's where my question began. So some of these proteins have a selenium while some of them have a cysteine, that is a sulfur. And why is it so? So that's where the evolution story began. So it might have been that 16 billion years ago when this protein started evolving, some of them had sulfur in them, some of them had selenium in them. And not just this switch, there could be other mutations which could be there in this protein that helps it perform the function. It could be a different function when the mutations change, or it could be the same function. So that's where our questioning began, and that's where we actually developed the molecular modeling technique to understand that. So what is computational modeling? Computational modeling involves simulations. Again, a difficult word. Okay, there's nothing to be scared about simulations, because simulations are just artificially preparing something where you can check the movement of a protein. Okay, so we have this protein structure which is made up of sequences, and those sequences actually have mutations in them. After COVID-19, people have really been interested in mutations. People want to understand more about it. So that's why we do this. So we give this input in the computers, and then we model it. So what do we model? First, we model the reaction. We actually see the reaction in the computers, and we also try to understand how is the protein moving. So we try to understand how is the bond moving, how is the atom moving, and then we try to get some results out of it. Now, how does this help? So this helps us to understand if the movement actually changes when there are different mutations in the protein, or is the protein stable. So we want the protein to be stable even if there are different mutations, and see if the protein, if it can give us good enzymes, and that's what we want to understand. So when we do these kind of techniques, these kind of simulations, we understand that the protein is moving at what rate, if it is stable, it is not stable, how is it moving. Well, we have these kind of graphs that you can see here. These kind of graphs help us to understand that more and more. So what I think is, after doing all these computational modeling and understanding the simulation of the protein, it can give me an idea about how this protein behaves, or what is the function when there is mutations, or when there are no mutations, and it can help us understand the oxidative stress which is related to this protein. Thank you so much.